Hello everyone, I'm back here with Irodov's Physics Solutions. This time we are taking these questions 3.197 in section 3.4. What we are given is this resistor network R1 and R2. The values are given 20 ohm and 30 ohm, and then there is a load resistance R3, and we need to find out what value of resistance Rx, we are calling it Rx, will the thermal power generated in it be practically independent of small variations in that resistance. You're not considering the extremes of Rx. For example, Rx is not short, Rx is not open, but there is some small variations around it, and for that small variations, the thermal power generated in Rx must be independent of that resistance changes, and we are supplying it with some voltage source. Let's call it V. So the normal way, if you do it using the Kirchhoff voltage law or the Kirchhoff current law, is to set up the two loops and find out the currents flowing in this loop and current flowing in this loop, and eventually you can find out either the current flowing in this resistor or you can find the voltage across this, and then you can find the apply either V square by R formula or I square R formula. But if you do this, because of these loops, it gets cumbersome. We will solve it with another trick or another technique, and I call it Thevenin's theorem. If you do not know about it, I will encourage you to go through the Thevenin's theorem lecture in one of my lecture series. So what Thevenin's theorem says that any circuit, let us say partition it in two parts. One part is this load, the other part is a complex circuit containing a lot of voltage and current source. Then you can replace this whole thing with a simpler equivalent circuit on the left hand side of this partition, such that we call it V Thevenin and we call this resistor R Thevenin. And then we can, with this simplified circuit, it will be easier for us to do the calculation. The only question is how to find this V Thevenin and R Thevenin. For this, Thevenin gives the second and third steps. R Thevenin can be found by shorting these voltage sources, looking into this from this area, look at this whole circuit on this two side from this side and short all your voltage sources. So this is just to find the R Thevenin. I have shorted this voltage source and my resistors are R1 and R2. I am looking at this from here. This will be our R Thevenin. So you look at this, then this R1 and R2 are in parallel. So our R Thevenin is equal to R1 parallel R2, or we can also write R1 R2 divided by R1 plus R2. Now how to find? So we have found this part. Halfway, we have done halfway. How to find the V Thevenin? For this, Thevenin says, connect the whole circuit is it, remove that load, you get a circuit like this. This is R1, this is R2, and this is our circuit. Now find the open source, this voltage across these 2 points, that will be your Thevenin's voltage. In this case, this voltage V will be divided in these two resistors R1 and R2 in the ratio R1. So the voltage here will be equal to, let's call it V Thevenin directly, will be equal to R2 divided by R1 plus R2 multiplied by V. So we know V Thevenin, we know V R Thevenin. Our problem should be simplified now. Let me remove these two. Let me remove this circuit which we have used. Now with this one, what our problem now is? Our problem now is to find out the the current, the energy in R Thevenin. And for this, now this V Thevenin is divided into R Thevenin and Rx. Since R1 is constant, R2 is constant, let's make it R Thevenin itself and try to find out what is the value of the energy in this one. That will be voltage energy in Rx. Ex will be equal to voltage as x square divided by Rx, and voltage on this resistance R will be equal to this Thevenin's voltage Vth multiplied by Rx divided by Rth plus Rx, this whole square, multiplied by 1 upon Rx. Because V Thevenin creates a voltage divider, and this voltage here will be Rx times V Thevenin divided by Rth plus Rx. This is what we have done. Now we can substitute these two values here, and we get V Thevenin is R2 divided by R1 plus R2 multiplied by Rx, whole things squared, divided by R Thevenin plus Rx, which is R1 R2 divided by R1 plus R2 plus Rx. This whole thing is squared multiplied by 1 upon Rx. And in that, what we will do is R2 square Rx divided by R1 R2 plus Rx multiplied by R1 plus R2, this whole thing squared 1 upon Rx square I have to cancel. It does not look a little bit of symmetry, so let's check it. I have only R2 here and R1 here. So in Thevenin's, probably Thevenin's voltage is the culprit. R Thevenin is right. V Thevenin, the open circuit voltage here, it will be R2. Let's keep on. So this is our energy formula. Don't find anything. And for this energy to be independent of this, we want the variation to be minimum. We will differentiate it. Dex is E upon Drx equal to 0. That will give us the denominator minus differential coefficient of this into R2 square minus differential coefficient of this take this one thing out, this square out. So we have R2 square, and R2 square is also out. So actually this R2 square should not enter into the term because this is constant for the differentiation. But we can remove R2 square here and we get R1 R2 plus Rx into R1 plus R2 minus 2Rx into R1 plus R2 will be equal to 0. So R1 R2, this gives R1 R2 minus Rx into R1 plus R2 is equal to 0. This implies Rx is equal to R1 R2 divided by R1 plus R2. And this is our answer. What does that mean? That the energy does not change for a small volume, for small variation in Rx. Let us say we have plotted this Ex somehow, and this varies with Rx, something like this. Then around, if you have this at this point, then if you change this Rx a little bit, then this energy will be changed by like this. But if you are right at here, then if you make a small change, then this corresponding change in this energy will be less. So we have in this problem used the Thevenin's theorem to derive this result, but this problem can also be done without applying the Thevenin's theorem, and I will show you some brief of how you can possibly proceed about that if you want to do without the Thevenin's theorem. If you do without the Thevenin's theorem, then the equivalent resistance, this circuit translates to R1, and this becomes R1 R2 Rx divided by R2 plus Rx. This is voltage V. And then we can find the voltage across this as V. No, this is not going to, okay, this is, let's say V across this resistor will be equal to this resistance R2 Rx divided by R2 plus Rx multiplied by R divided by R2 Rx divided by R2 plus Rx plus this resistor R. So all we have done is find the voltage across these two parallel resistors, which will be the same on this resistor as well as this resistor. And we can simplify this a little bit. R2 Rx plus R, this is R1, plus R1 into R2 plus Rx divided by, this terms cancel on the top and bottom, we have R2 Rx plus R1 R2 plus Rx R1. Basically these, some mistake here. No, that we are fine. This is the voltage across. This becomes same on the top and bottom, so something is wrong. So R2 Rx into R. This term will be R2 Rx into R, R1. Now we know the voltage across this. What we can do is the energy will be equal to V square by R. So we can write R2 Rx, this is Rx, into R1 divided by R2 Rx plus R1 R2 plus Rx R1. This whole thing is squared. This whole thing is squared multiplied by 1 upon Rx. And now you can remove one of the Rx. You should be able to get results which was same as in the earlier one. It is pretty much same whether you do it with the Thevenin's or without Thevenin's. There are some calculations involved, and the key thing is find the energy into it and differentiate it with respect to Rx.